Before men ever set foot on the moon, the world watched with awe and anxiety as the United States and the Soviet Union raced into the stars. In April 1961, Yuri Gagarin became the first human in space orbiting Earth and instantly becoming a global hero. Just 1 month later, America responded with Alan Shepard's flight, but his mission lasted only 15 minutes. At that moment, the US seemed far behind. Yet, less than a decade later, American astronauts walked on the lunar surface. How did NASA leap from short suborbital hops to the most ambitious mission in human history? The answer lies in two early programs that laid the foundation, Project Mercury and Project Gemini. These programs may not have captured the world's imagination like Apollo did, but without them, Apollo would have been impossible. They were the training ground, the place where technology was tested, mistakes were made, and lessons were learned. Today, let's step back into those crucial years and explore how these two projects prepared NASA for the moon. NASA, as we know it, is not as old as it might seem. It was officially created in 1958, a direct response to the Soviet Union's launch of Sputnik the year before, but NASA wasn't built from scratch. It was formed by combining existing institutions, the National Advisory Committee for Aeronautics, parts of the US Army's Ballistic Missile Agency, and even a number of German scientists who had worked on rocketry during World War II. The US Air Force also had its own effort called Man in Space Soonest, which was handed over to NASA, along with facilities and staff. Together, these became the backbone of the new agency. At the same time, experimental aircraft were pushing boundaries. The X-15 rocket plane skimmed the edge of space, reaching altitudes above 100 kilometers and speeds over 7,000 kilometers per hour. These were astonishing achievements, but the X-15 could not achieve orbit. It was clear that if America wanted to send humans into space and eventually to the moon, it would need something entirely new, a spacecraft that could survive launch orbit and return. And so NASA's first true human spaceflight program began. Project Mercury was America's first attempt to put a person in orbit and bring them home safely. The goals were simple to state, but incredibly difficult to achieve: launch a human into space, keep them alive, and recover them safely. Imagine being one of those early astronauts knowing you would sit atop what was essentially a modified missile. The Redstone and Atlas rockets had originally been designed for war, not for carrying people. Vibrations, G-forces, and the risk of catastrophic explosion were constant threats. Even if the rocket worked, astronauts would face extreme radiation, micrometeoroids, and the fiery gauntlet of re-entry, where temperatures soared to 600 degrees Celsius. NASA engineers developed ablative heat shields that burned away during re-entry, carrying heat with them. They designed escape systems to blast the capsule away from the rocket if something went wrong, and they built the Mercury capsule itself, a small pod barely big enough for a single astronaut with parachutes for ocean splashdowns. The road to success was anything but smooth. The first test flight in 1959 barely lifted off the ground before collapsing back onto the pad. Animals were flown to test systems before risking human life. Only after more than 20 unmanned and animal flights did NASA finally approve human missions. But even with this preparation, the Soviets struck first. In April 1961, Yuri Gagarin completed a full orbit of Earth, stealing the title of first man in space. When Alan Shepard launched a month later, his flight was suborbital, important, but far shorter. For America, it was a moment of both pride and pressure. Over the next 2 years, Project Mercury completed 6 crewed missions. Astronauts John Glenn and others finally achieved orbits around Earth, proving that humans could survive in space and endure re-entry. Still, Mercury had limits. The longest flight lasted just 34 hours. That was enough to show survival, but nowhere near enough for a lunar mission. What Mercury did accomplish was critical. It gave NASA the confidence to send people into space, it tested rockets, heat shields and recovery systems, and it produced the first group of American astronauts men who would later play key roles in Gemini and Apollo. By 1960, even before Mercury ended, NASA had announced the Apollo program, an ambitious plan to land men on the moon. But looking at Mercury's capabilities, it was obvious how far they had to go. Apollo would require astronauts to live in space for at least 8 days, far longer than Mercury had allowed. They would need to master orbital docking, the delicate maneuver of joining two spacecraft in orbit. They would need to practice spacewalks working outside their capsules, and they would need precise control of re-entry, aiming for specific landing zones. All of this was new territory. Mercury had proven survival. Apollo demanded mastery. To bridge the gap, NASA launched an intermediate program, Project Gemini. Project Gemini ran from 1961 to 1966, and it was the true classroom for the Apollo astronauts. The Gemini capsule looked like an enlarged Mercury capsule, but it could carry 2 astronauts instead of 1, and it was equipped with an advanced maneuvering system called OMS, the Orbit Attitude and Maneuvering System. For the first time, astronauts could adjust their orbits and orientation in space. The missions gradually expanded human capability. By Gemini 5, astronauts spent a full week in space, proving long-duration flights were possible. Gemini 7 pushed the record further, 14 days in orbit, more than enough for a lunar mission. Living in such confined quarters for 2 weeks tested not only technology, but human endurance. Perhaps the most dramatic moment came with Gemini 8, commanded by Neil Armstrong. The mission's goal was to rendezvous and dock with an uncrewed target vehicle. The docking succeeded, a triumph for NASA, but suddenly the spacecraft began to spin uncontrollably. A thruster had stuck open, using fuel and threatening to knock the crew unconscious. If they couldn't regain control, they risked disaster. Armstrong, calm under pressure, undocked and fired the re-entry thrusters, finally stabilizing the spacecraft with just 30% fuel remaining. It was a narrow escape, but it proved the value of skilled pilots and redundant systems. Gemini also introduced spacewalks known as extravehicular activities, or EVAs. Astronauts learned the hard way that working in space was exhausting, with early spacewalkers struggling to control their movements. But with practice and innovations like handholds on the spacecraft, astronauts adapted. Buzz Aldrin set a record with a 5.5-hour EVA, showing that humans could indeed work outside in the vacuum of space. Over 12 missions, Gemini mastered every skill Apollo would need: long-duration flight, rendezvous, and docking and spacewalking. It also gave astronauts invaluable experience in handling emergencies. These were not just technical rehearsals, they were psychological ones, proving to NASA and the world that Americans could meet the Soviet challenge. Conclusion from Mercury and Gemini to Apollo, 160 words. Looking back, Mercury and Gemini may seem like small steps compared to the giant leap of Apollo 11, but without them, Apollo would never have left the drawing board. Mercury taught us survival. Gemini taught us how to live, work, and maneuver in space. Together they closed the gap with the Soviet Union and paved the way for the moon. When we watch the famous footage of Apollo astronauts setting foot on the lunar surface, it's easy to forget the countless tests, trials, and near disasters that made it possible. But in those earlier capsules, cramped, fragile, and unproven, the foundations of lunar exploration were laid. And so, as we celebrate Apollo's triumph, let's remember Mercury and Gemini, the essential stepping stones on humanity's path to the moon. If you've enjoyed this journey through the early days of spaceflight, make sure to subscribe to Cosmic Compass. There's so much more to discover: missions, mysteries, and the hidden stories of exploration. And if you'd like to dive deeper, there are incredible documentaries available that explore these missions in detail, showing not just the triumphs, but also the struggles along the way. Thank you for watching, and thank you to everyone supporting the channel. We'll see you next time as we continue our voyage through the cosmos.